This is an example of how to calculate the fugacity for a fluid actually close to critical conditions. We could use the data for HFC to calculate its fugacity. Let's say the fluid's at 4 megapascals at 110 degrees Celsius at conditions where we believe it may not behave like an ideal gas. So from the chart I've looked up H and S. The reason I've done that is because fugacity is related to Gibbs free energy. We'll call this condition 2 and say that the fugacity will be obtained once we calculate the Gibbs free energy, and we can relate the Gibbs free energy to ideal gas conditions. So first, to calculate the Gibbs free energy at the final conditions, if you like the condition of interest, notice I have to use absolute temperature. This is the entropy. The Gibbs free energy at 4 megapascals and 110 degrees Celsius is negative 213.8 kilojoules per kilogram. And so the way I'm going to use Gibbs free energy is I'm going to look at the differences where this is going to be the ideal gas case and this is going to be the condition we are interested in. So Gibbs free energy is related to fugacity by the log, and so if I could find the condition 1 where this is an ideal gas, and fugacity 1 would be pressure 1, and then I could get fugacity 2. At condition 1, I need the Gibbs free energy. Now at low pressure, where we expect to have an ideal gas, where we could keep the temperature the same because we're only calculating here for a pressure difference, the lowest pressure on the chart is 100th of a megapascal. So let's use that and let's look up H1 and S1. H1 being 504 kilojoules per kilogram, S1 at 2.32 kilojoules per kilogram per degree Kelvin. So Gibbs free energy 1 is 504 minus the absolute temperature, so 383 times 2.32, and this gives us a value of negative 361.4 kilojoules per kilogram. So if I go back to my equation for delta G, in G2 minus G1, that's going to be equal to negative 213.8 minus negative 361.4, the ideal gas value. So delta G is 147.6 kilojoules per kilogram. What we have to be careful about in substituting into this equation is that the equation we're interested in, you need to notice that the gas constant here. So we have to have the correct units, and we want a molar Gibbs free energy, and right now we have a mass-based Gibbs free energy. So what we are going to do is determine the molecular weight and use that with delta G. And since delta G is 147.6 kilojoules per kilogram, we multiply that by the molecular weight of 100 kilograms per kilomole, which is 15,055 kilojoules per kilomole. We can also write that as 15,000 joules per mole. Now then the delta G is RT natural log of fugacity 2 or fugacity 1, so delta G ends up being 15,055. And this equals 8.314 joules per mole degree Kelvin, using the temperature of 383 Kelvin. And the log of fugacity 1 is just the pressure, 0.01 megapascals. And then when fugacity 2 is solved for, I get a value of 1.13 megapascals. And this is at 110 degrees Celsius and 4 megapascals.